good evening.
Good evening.
All right.
All right. Thank you, by the way, sir, for following up on yesterday's query. I appreciate it. I know it was Sunday and everything, so
I try my best. I try my best in order to be able to answer such questions, especially questions by part timers, because I know the weekend is more the time which you have available. Obviously, if I don't reply exactly on Sunday, then I try to reply the following morning, usually. Um, so yes,
thank you.
I,
Appreciate it.
it's fine. Okay, Mela. Right, we're just waiting on Floyd, Gary, and Glenn, but we should be able to start. I think they're about to join us anyway. So, hello. Right. So, good evening, everybody. Welcome to our last lesson for this particular topic. Okay. Hello. What we're going to be discussing today is data storage in a bit more detail. I'm going to skim over the stuff that we've already discussed in introduction to computing, an introduction to computer architecture. The reason why they might seem similar is because that, technically speaking, this course can be taken in isolation, and therefore there might be some element of repetition. So obviously, where there is some repetition, I will gloss over. But I will focus primarily more on the stuff that we've already that we haven't yet talked about. Then we're going to switch tact, and we're going to talk about operating systems in relation to memory management, process management, and I/O management. Okay, so without further ado, and so that we don't end up finishing too late. Okay, let's start off with our lecture with regards to data storage. So, essentially, with regards to data storage, again, we're going to be focusing primarily on hard disks and optical media. All right. So remember that when we talk about hard disks, we're talking about a number of we're talking about the mechanical hard disks where you'll have one or more disks, all right, which are coated with a magnetic material that are spinning around the central spindle, where each surface of the disk, all right, from top and bottom, all right, would have its own read and write head, and each read and write head is in turn connected to a center arm, all right, which means that all of the read and write heads are on the same track, all right, when the arm is actually moved. Essentially, if we had to look at the construction or a diagram of a construction of a hard disk, all right, you'll see that we have our platters over here, all right, with magnetic material on either side. All right, we have our spindle, we have our arm assembly with a read and write head for each surface of the platter. All right, our hard disks include circular tracks all the way around the hard disk. The smallest segment that we can actually write to is known as a segment, okay, and the segments that fall or along the same track, all right, on all surfaces is known as a cylinder, all right, essentially. And the way that we read data or we write data is that this spindle is constantly turning, all right, and the read and write head sort of like pivots in and out in order to access all of the tracks on all of the heads at any given point in time. This is essentially what it would look like internally. Now, it's worth pointing out that in the normal design of a hard disk, all right, hard disks would split up each track into sectors, and in the older systems or in the older hard disks, the sectors in the center were by far smaller in terms of real estate than the sectors towards the outer edge of the hard disk. All right. In fact, the data density towards the center of the hard disk was by far greater than the data density towards um, the outer edge. However, this form of data density distribution has actually changed with the invention of more efficient hard disk designs, meaning that you can actually store a lot more data onto the hard disk itself. Right. So, when we talk about a sector is essentially the smallest addressable block that we have for our hard disk. All right. However, it is very much the case that the data that we might be writing to the hard disk would make use of multiple sectors. All right. Um, which we can consider as being clusters. All right. Essentially, a cluster are basically a number of contiguous or joining, if you will, sectors that exist on a hard disk. All right, and essentially, when you're writing data to the hard disk, you would be writing to these clusters. All right, so essentially, as we can see, each one of these circular the sort of for example this circular path highlighted in red is known as a track. All right, what we have here highlighted in the blue region, all right, that is known as a sector. What we have here highlighted in blue, all right, the entire region B, that is known as a geometrical sector. And when we have a number of sectors one after the other, that is known as a cluster, essentially. Right. One thing that we need to take into consideration when we talk about hard disks is that hard disks tend to rotate at what is known as a constant speed or constant angular velocity. All right. Essentially, what that means is that it takes the same amount of time to cover the 360-degree spin at any given point in time. All right. This means that if your head is on the outer tracks rather than the inner tracks, then the data that is actually passing underneath the head is actually traveling at far higher speeds than the data that may be passing over the heads in the inner tracks. If you think about it, all right, if you have a pivot point here, okay, think of a door, if you will, all right. A door has a hinge, all right, and the door itself, or the frame of the door, or where you have your handle most of the time on a door, all right, tends to be at the edge. The amount of displacement that you get with the door handle, all right, is by far more the distance that is actually covered with the part of the door which is closer to the hinge. All right, the same thing can actually be thought of. All right, when we're talking about the sectors, all right, on a hard disk, since our hard disks are spinning at a constant angular velocity, then it means that the number of sectors on the smaller tracks, all right, have a higher are traveling under the head at a slower speed, rather than those that are on the outer tracks. As we have multiple platters.
Sorry. Slower
Yes.
on the outside, no?
Around the outside, it actually travels a lot faster.
Is it
than
quicker? Alright, so it's quicker on the outside then.
The amount of data or the amount of space that is actually traveling around on the head, all right, that is quicker. Yes.
Alright, thank you.
All right. Especially with the newer hard disks, essentially, are quicker read and write heads, essentially, which can vary their read and write speeds depending upon where the head happens to be. The reason is so that you would have a similar data distribution or density distribution across the entire platter. All right. So essentially, it would write and read at a faster rate on the outer tracks, all right, than it would write and read on the inner tracks, essentially.
Alright.
Okay. At least that's what modern hard disks do. Okay. Now, since we have multiple platters, we have multiple tracks, and therefore we have multiple sectors. All right, it makes sense that we need to have some form of a system that allows us to access any point in our hard disk in order to be able to read the files or the data that we're actually storing on these hard disks. All right, one of the ways that we can actually use in order to address a hard disk is what is known as CHS addressing, which is a synonym, or rather an acronym, for cylinder, head, sector, addressing. Essentially, the cylinder is going to determine which track number you're trying to access. The head is going to determine which surface of which platter you're actually going to be reading from. And the sector number is going to indicate which sector you want to read. So therefore, you can have a CHS number of being 3623, meaning the cylinder, which happens to be on surface 6, which is on sector 2. All right. Essentially, this provides us with a neat way of being able to read um, to read this data. So essentially, what would happen with this particular number is that the head will have to move over the cylinder in question. In this case, cylinder 3. All right. It will then wait for the sector of that particular head, being head 6 in this case, all right, to come underneath underneath the read write head, all right, and when sector 2 comes along, it will just read that information, or it will write data to it. Okay. The problem, obviously, with this particular system is that that the geometry of the disk must be known beforehand to the rest of the system in order for one to actually be able to address in this way. All right. It also it would also limit, all right, the amount of data that you're actually storing on each sector. All right. And therefore, you would get this uneven distribution of data density across the entire disk. So one way to alleviate this is to use what is known as logical CHS addressing. Essentially, what you would do is you would have internal electronics which will take care of mapping the logical CHS address into an actual sector address. Essentially, what you're doing is you're hiding away or you're abstracting away the internal geometry of the disk to the rest of the system, therefore acting more of a black box, essentially. All right. So that basically means with this addressing system that you would be able um, to have a simplified method of actually accessing data. Another thing that you can actually do over and above that is to use what is known as linear addressing. Essentially, what you would do is you would literally number, all right, the sectors or blocks rather, from 0 to a maximum number on each on the tracks itself. Essentially, you would create a one-dimensional array, all right, where each block is of the same size, all right. So when you're addressing block 0, for example, block 0 is on the first track. Whereas if you're addressing block 20, that's on the, for example, third track, and so on and so forth. Okay? Essentially, you would use this logical CHS addressing in order to be able to map, all right, where the head should move in order to read the data or write the data that you want to do to write at that particular location. All right. So this is essentially what CHS addressing looks like. So notice each track has its own number. All right, as well as each sector has its own number. But notice as you go outwards, all right, the sectors become larger and larger and larger and larger, therefore having less efficiency or data efficiency across the entire platter. This is what CHS addressing offers. The linear addressing method combined with the logical CHS addressing uses something which looks like this. Notice that the size of each block of data that you have over here is relatively the same size, all right, physically and in terms of data, all right, across the entire surface of the disk. Notice that each block is numbered, so you have 1, 2, 3, 4, 5, 6, 7. In this case, up to 11 for the smallest track, and then it continues. It continues from here 12, 13, 14, 15. Notice that they are in very close proximity to each other, and it keeps on going and going and going and going. All right. This is obviously more efficient in terms of the way that data is actually stored upon the hard disk, all right, as you can imagine. So, as we have already mentioned, hard disks have multiple platters stacked on top of one another, all right, and as we said, we have a read and write head per surface, which, as we also mentioned, they tend to move in tandem, all right. So therefore, if we have a head that needs to read from track 13, for example, that means that all of the heads happen to be on track 13 at that particular point in time. That's why we call it a cylinder, okay? If we take a look at hard drives nowadays, all right, they are more often than not made up of multiple platters. Gone are the days when they are actually made up of just the one. All right. Again, here's a more of a graphical representation of what a sector, a cluster, a track, and a cylinder actually represents with regards to multiple platters. Right. So the hard disks themselves, all right, are actually constructed of, as the term implies, very hard materials. In fact, the discs themselves are made up of aluminium or nowadays even glass. All right, and they have a coating of metal alloys in order to give it those magnetic properties. Typically, hard disks tends to spin at very high RPMs. All right, usually when we talk about laptop hard disks, they usually tend to spin at around 5,200 RPM, but it can even go up to 12,000 RPM, really and truly, for the more high performance hard disks. All right, it's not unheard of to have hard disks that rotate at around 12,000 RPM. All right, and essentially the heads tend to hover over a cushion of air, all right, between the head itself and the hard disk, all right. In fact, the head does not actually touch the hard disk itself, but the distance between the head itself and the surface is very, very, very small. In fact, when you actually are building a hard disk, they actually create it in a hermetically sealed and free of any other contaminants, because it's very, very easy in order to create contaminants that might actually damage the surface. In fact, if we actually had to take a cross-sectional sort of look, this would be the head, all right, that we have over the platter. This would be literally the distance between the head itself and the magnetic surface that we have. And these are essentially different sized objects. So over here, we'll have this would be a smoke particle. This essentially would be sort of like the oily residue that you would leave with a fingerprint. This would be a dust particle. And this here would be the size of a human hair. So as you can see, the tolerances are very, very, very small. That is why it's not a very good idea to carry a laptop which is running on a mechanical hard disk around whilst it is still on. But why? Because every time you're moving, essentially the chances of the heads actually colliding with the surface actually increases. In fact, if that happens, then you could actually get something known as a total head crash, where all of your heads would have literally scratched the surface of the hard drive beyond all repair, essentially. All right, this is one of the main drawbacks of these types of hard disks. All right. What about error handling? Hard disks also include what are known as error correction codes. Essentially, these are some form of extra bits that are dedicated to each block of data, which is determined mathematically in order to allow for some form of data recovery, especially with regards to um, uh, to data corruption, all right, on the magnetic medium itself, all right. Station information with respect to other sectors that relate to a particular file, and the tailor essentially will contain the error correction code in order to make sure that the data that is stored is actually maintained between them. Notice that since we're also talking about a magnetic material, all right, as you know, magnetic materials which are very close to each other can actually affect one another. So, in reality, all right, there happens to be an intersector gap as well as an inter-track gap between one block of data and the next. Essentially, that gap, all right, is necessary in order to reduce the amount of interference or magnetic interference between one portion of the hard disk and the next. All right, obviously, in this diagram, that gap is exaggerated in order for you to be able to understand what we're talking about. All right. Was there something that you didn't understand that you would like me to reiterate, please? Floyd.
Actually, the stream during the previous slide, at least for me, it's cut off and I didn't get anything from the previous slide.
All right. So essentially, what I was saying is that that since we are working with magnetic materials on a hard disk, it is and since magnetic spots on a hard disk can tend to affect each other. All right. If you have two magnets which are close to each other, they would tend to interact with one another to a certain extent. You know, which can essentially, in the case of a hard disk, it can actually corrupt the data that we have within it. All right. In order to reduce the possibility of that happening, is that for every block of data on each sector, you would have what is known as an error correction code, okay, which is stored within the tail end of the sector, okay. So for each block of code in the sector, all right, you have a tailer containing the error correction code. You also have a header so that you'll be able to link different sectors to have files maybe even scattered across across the hard disks, essentially. Okay, so you'll be able to say, all right, this data here is related to another sector over there, which is related to another sector over there, and so on and so forth, in order to encompass a file. But more over than that, all right, what is also introduced between each sector, you would have this inter-sector gap, all right, and between each track, you would have this inter-track gap, all right. So between one sector and one track and the next, you would also have a gap in order to limit the amount of interference that you might have from one sector to the next, essentially.
All right, thank you, sir.
Okay, that's essentially what I was talking about. Are there any other questions?
None, thank you.
All right.
On my end.
Okay. So, what about access times? So, whenever we talk about access times with regards to hard disk, we need to take into consideration a number of different aspects. All right. Essentially, when we're talking about access times, we're talking about the amount of time that it actually takes for a hard disk to read or write a particular area on our hard disk. Essentially, access time really and truly refers to the amount of time that we actually take in order to reach that particular position that we require. However, the access time can also be then split into two different categories. You have the seek time, all right, which is essentially the amount of time that it takes for one to move the head over the required track, and then you have the rotational latency, which is the amount of time that it takes for the head in order to fall underneath the head so that you can actually read it, all right, or rather perform some form of data transfer. All right, so this is access time, sort of like split diagrammatically. So you have your seek time, where your head is actually moving to the required track. All right, this is the desired block that you want to read. So you have to wait for that desired block to come underneath the head so that you'll be able to do your data transfer. All right, so that would be your rotational latency. And essentially, once you are reading or you're writing, essentially you get what is known as your transfer time. So that is essentially what compromises your access time. So essentially, when we talk about rotation latency, we're literally talking about the amount of time, all right, that the desired the desired sector is actually going to come underneath the head. And notice that this amount of time is not going to be fixed, because at best, once you exactly move your head over the required or the desired track, the desired sector happens to pass underneath the head. All right. At worst, all right, when you moved your head, all right, the desired track happens to just pass underneath the head. So you'll have to wait it to go all the way around again, all right, in order for you to be able to read it. Therefore, the rotational latency is essentially going to be inversely proportional to the disk's rotational speed, all right? So the way that we calculate it, all right, is going to be by taking the RPM, all right? In this case, let's say that we have a hard disk which has a 10,000 revolutions per second per minute, sorry, 10,000 revolutions per minute rotation and speed, all right? To convert that into rotations per second, all right, we'll have to multiply that by 60, all right? So 60 all over 10,000, all right, is going to give you the rotation speed in terms of seconds, all right? If you halve that in order to get the average, all right, that would mean that it will take, on average, all right, 3 milliseconds in order to reach any sector, all right, on your hard disk. Okay, essentially, once the head has actually arrived at a particular track. All right. So another factor that we talk about when we talk about hard disks is the idea of the seek time. All right. Now, the seek time is essentially the amount of time that the head is spending traveling from one track to the other. All right. Now, the seek time, unfortunately, is not as easy to calculate as that of the rotational latency. All right. Notice that the head movement, really speaking, is very, very, very slow since it is mechanical. All right. So it makes sense to try to minimize the amount of movement your head is going to be doing at any given point in time. In fact, if you have hard disks completely fragmented, all right, meaning you have files split up, all right, and placed in various literally random sectors along the entire hard disk, it means that your hard disk is going to be moving a lot, meaning that it's going to slow down your system. All right. So what you would do is you would need to defragment your hard disk, all right, which essentially means reorganizing your hard disk in order to place files or sectors of into a particular file close together. All right, therefore making it easier to read at any given point in time. In fact, with newer operating systems, all right, so I'm talking from Vista onwards, this form of disk defragmentation was actually included, all right, at least with Windows operating systems, to be done in the background whilst the computer wasn't actually doing anything computationally heavy. So essentially, the computer was constantly trying to defragment your hard disk in order to make sure that your computer was running as fast as possible. Obviously, unless you disabled that particular feature yourself. All right. in older operating systems, you needed to make sure that you schedule the particular time for this defragmentation. That obviously takes a lot of time. All right. Another factor that determines also the speed at which one can actually read or write to a hard disk, all right, is what is known as disk scheduling. Essentially, disk scheduling, as I mentioned before, is the idea of trying to minimize the amount of travel for the head. All right, if the head moves less amount of time, all right, it's going to be able to read and write data a lot faster. Disk scheduling essentially gives examples or gives strategies, if you will, as to how the head should behave in order to be able to access the required or the selected blocks of data. All right. This can be done in a number of different ways. One way is what is known as the first come, first serve implementation. So let's assume, for example, that we are trying to read sectors 8, then 6, then 20, then 14, then 26, then 10. Essentially, what we're telling is the hard disk needs to move across these tracks in order to reach those particular sectors. All right. As we're going to see, this amount or this disk scheduling technique is going to make our arm move about 6 times more, all right, than another technique, which is essentially something that we're going to be discovering in a short while. So let's say that these are the tracks or the sectors that we're talking about. So let's say that we are on sector 8. All right, so we've read that. Okay, we now want to read sector 6. All right, so notice our hard disk needed to revolve all the way around and move our head outwards, all right, in order to be able to read sector 6. All right, then we need to read sector 20. All right, so sector 20 is on this track over here. All right, which means we have to move our head inwards and we have to rotate our disk as well. Then we need to read sector 14. All right, so move it again outwards. All right, sector 26, move it again inwards, and then sector 10 again, move it again outwards. So as you can see, our head is actually moving literally for each sector that we actually need to read. All right. Another technique that we might want to employ is the shortest seek time first approach. All right. Essentially, what you would do is, if we take the same requested sectors, we would organize them in a way, all right, that we would actually read the sectors which are closest to where my head currently happens to be first, and then move towards the sectors which are further and further away. This would reduce our arm movement quite significantly. So as you can see, all right, we are reading sector 8 first, then we're reading sector 10. Notice our head remains in the same location, and then we're also reading sector 14. All we're doing is waiting for the disk to spin. All right. Then when we're reading sector 6, we move our head once more, all right, in order to read sector 6. And then when we want to read sector 20, all right, and sector 26, we'll move again, all right. So essentially, if we had to plot, all right, the amount of movements that our head would actually need to do with regards to our first come first serve methodology, all right, as opposed to our shortest seek time first operation, you would notice that the amount of movement is by far reduced. All right, therefore making it less erratic. All right, and the amount of movement is henceforth reduced. Okay. Obviously, all of this is all well and good. However, hard disks need to be formatted, all right, before you can actually place any data upon the disk at any point in time. All right, most modern hard disks come pre-formatted. However, it's very, very possible that you would need to do a format yourself before you actually start making use of the hard disk itself, and you probably would need to format the hard disk, especially if you're going to make that particular hard disk a bootable drive. All right. Notice that when we're storing files on a hard disk, all right, it is not unreasonable to think that files are stored across different sectors or across different blocks on your hard disk. All right, so it is very possible that whenever you're trying to access a file, you would first need to access a directory, and then each and every block that you would need to access will then link you to the next block, to the next block, and to the next block, and to the next block. This is why, all right, whenever you throw away a hard disk, all right, and whenever you perform a quick format, essentially what you're doing with a quick format is that you're not really and truly deleting the data that happens to be on your disk. All you're doing is deleting this directory file. So essentially you're deleting all of these pointers to the first block of data that happens to be to each and every one of your files. If you delete this directory, all right, zero it out essentially, then what that means is that your hard disk thinks that there's nothing on your hard disk, when in really and truly you actually have the data over there waiting for you. That's why there exists software that is actually able to retrieve data that is seemingly lost, all right, on a hard disk, all right. And that's also why whenever hard disks with yes,
Would the data be overwritten then in time? Because if it
yes, eventually, yes, it would be overwritten in time in that case. But sometimes when what I was trying to say was that when you have companies, maybe even government entities that are maybe thinking of replacing their computer systems, all right, when it comes to hard drives, they don't just format them and throw them away. They usually destroy them with hammers so that they can't actually be accessed anymore. Because, as you can imagine, certain certain data of certain agencies might be worth a lot of money in the wrong hands. So that is one of the reasons why they would tend to do that in order to safeguard themselves from being held for ransom, essentially, at some point later in the future. To Paul. So whatever you do, all right, whenever you're trying to get rid of a hard disk, if you really want to make sure, all right, that any personal data that you might have had on that hard disk does not fall into the wrong hands, make sure that you destroy it well. All right. Just saying. Okay. Again, obviously, when it comes to performance, all right, the more scattered they are on the hard disk, the more time it's actually going to take in order to read that particular file. What disk defragmenting will actually try to do is actually try to place these blocks of data in a contiguous fashion, essentially. But obviously that would require you to perform a disk defragmentation. Okay. All right. We've talked a little about hard disks. Let's talk a little bit now about optical storage. Essentially, as we know, optical devices or optical drives make use of a disk, and they use a laser in order to read and write data to and from this disk. All right, as we discussed in previous lectures. All right, even in the first term, a CD-ROM is made up of lands and pits. All right, lands being flat areas and pits being indentations, small indentations, which when shone at by a laser, all right, the laser would be able to differentiate between these two and therefore be able to identify ones and zeros within the data itself. All right, this should trigger a bit of memory of what we had actually covered in a previous lecture. All right. We also talked about the differences between CD-ROMs versus CD rewriters. Obviously, this same thing applies with DVD-ROMs and DVD rewriters, or Blu-ray ROMs and Blu-ray rewriters, where essentially, whenever you are writing data to the disk, all right, with these rewriter technologies instead of pits and lands, what essentially you're doing is you are modifying the opacity, all right, of the outside layer of the disk, all right, and the difference in opacity, all right, and whether the laser is actually going to reach the reflective layer or not, all right, is going to determine in this case the ones or zeros. And again, all of the data that is stored on these optical media is stored on one spiral track, essentially. There is no idea of separate tracks, all right? There is just the one track going in a spiral fashion all the way out from the center, all the way out to the exterior of the drive, all right? Again, this is a little bit of a reminder of what the structure of a ROM, an optical drive, will actually look like. So essentially, you would have this polycarbonate surface, all right, and then you would have your reflective surface over here, a thin layer of varnish, and then you would have your artwork, all right, or your disc, disc artwork. Usually with CD-ROMs, you'd have your laser that is actually shining through this polycarbonate layer onto the layer with your pits and lands, and that is reflected back into your optical sensor, and therefore you'd be able to read ones and zeros. With the rewriter drive, essentially what you're doing is you're changing how transparent this surface happens to be. That's why CD rewriter or rewritable material tends to be less less durable than CD-ROM or ROM drives, essentially. Right. So since our CD or since our optical drive is made up of a single spiral track, all right, it it also would require some form of addressing. Now, in a very similar fashion to the hard drive, all right, you would split up each segment along this spiral, all right, into sectors so that you would be able to identify which part of the track you would actually need to read, and each sector would include a number of different aspects. So you'd have a sync field, usually around 12 bytes, all right, which essentially indicates the start of the sector, all right. You would have your header, all right, which is usually used to identify the sector. You would have your data, all right? So essentially you'd have where your data is actually being stored, and then you would have yet another 28 bytes of error detection and correction code, like you would have within a hard disk, all right? Essentially, the idea behind this error detection is so that if there are some minor faults, some minor scratches on the surface of the hard drive, all right, you would be able to recuperate, all right, the data that might have been misinterpreted upon reading, all right. And again, the whole the whole point is so that you would have built some more resilience, all right, into the media itself, all right. Whenever we talk about reading and writing speeds, all right, sometimes you might have seen them, maybe even on the drive itself. You'd see 1x, 8x, 52x, and so on and so forth. The um, that value, all right, that x value is essentially the amount. It relates to the speed of your drive, all right. Essentially, when we talk about a 1x speed drive, that basically means that we have a drive that can read up to 75 consecutive sectors per second, all right. A 52x drive will do 75 times 52. Essentially, that's the only difference between one and the other. All right. Now, unlike the the hard disk, all right, an optical drive would tend to spin at what is known as a constant linear velocity. That means that that the data that is actually traveling, all right, on the outer track and being read by the laser is of the same density as those that are in the small the innermost part. So essentially, when the head happens to be on the outermost area of the disk will tend to slow down. Why? Because when it's slowing down, all right, it will allow, all right, for the data to be read, all right, at the same rate as when it's towards the center. In fact, if you move your head towards the center, then the disk will speed up essentially. All right. In fact, if you have ever heard, all right, a disk drive, you would actually hear it spinning up, revving up and revving down, depending on where the CD head happens to be reading from, essentially. All right. So essentially, as you move towards the edge, all right, the revolutions per minute goes down. As you get closer towards the center, the revolution per minute goes up. Again, the idea behind that is so that the data density along the entire disk is uniform, all right? And since the data density is uniform across the entire disk, therefore, one can also assume that the transfer rate is uniform. Okay. So essentially, whenever we're talking about an optical drive with a particular speed, really and truly, we're not really talking about. That's why we can't talk about revolutions per second, really and truly, because at a particular position, all right, the disk is going to be spinning faster. At another position, the disk is actually going to be spinning slower. In fact, a 1x speed motor would decrease from 492 RPM all the way down to 221 RPM. All right, as you move towards the center. All right. Now, whenever you're trying to read from your disk, all right, what the what the optical drive will tend to do is it will tend to guesstimate, all right, the location of the required sector. In fact, what happens is that the laser head is moved to roughly the correct position, all right, and you would notice that different regions along the hard disk will have what is known as a zoned constant velocity. Essentially, the velocity is not literally linear, and you would, if you move it 1 millimeter, it will have to actually speed up. All right, you would have sort of like steps, all right, of velocity across the length of your hard drive. All right, the idea is so that you would have something which is close to having literally a constant linear velocity in and around those particular regions. All right, usually with a 52x drive. All right, the the innermost zone would be rotating at around the outermost edge of the of the disk essentially would be spinning at around 20x speed, whereas if you move progressively inwards, it will be moving at 20x speed essentially. All right. So how does the drive actually access the data on your optical media? As I said, the optical media doesn't actually know directly the exact position of where the sector that you would like to read resides. However, you would have a good idea and approximate areas to where that sector happens to be on your disk. So what you do is you move your head to that approximate area. All right. The speed is then adjusted, all right, in order to be able to read in that particular block. You would read the first block that comes over the head, all right, and let's say that it is block M, all right, but the block that you want may be the block would be a value which is bigger than M. If that is the case, then you would adjust the head accordingly. All right. If it happens to be exactly the sector that you are required, then great. But it could be the case that you would need to move the head slightly in order to adjust and reach the data that you are trying to access. Again, all right, this would mean that the exact amount of time that it actually takes in order to read any sector on your optical media is relative. All right. In fact, this process results in the seek times to be quite slow when compared to, say, a hard drive. In fact, it is measured in the seconds rather than in the milliseconds, like we saw with the hard drive. All right. The main difference between different media, all right, is essentially within the wavelength that is used, all right, between the media. So a CD-ROM uses a red laser, all right. DVD uses a laser with a shorter wavelength, all right. In fact, the DVD wavelength is 650 nanometers as opposed to the 780 nanometers for the CD. Blu-ray discs, on the other hand, all right, actually use a laser wavelength of around 405 nanometers, which means that obviously you have a much finer point that you would actually be able to read than, say, a DVD. And in fact, the the lasers for these different media tend to span different spectrums of light, and therefore make each of these media more capable of storing more and more data. In fact, the shorter the wavelength, the more and more data you can actually store on that same disk. All right, on the same real estate, you'll be able to store a lot more data. All right. In fact, you would probably remember this diagram that I had shown you in a previous lecture. All right, showcasing the size, as you can see, of each of the lasers that we had talked about, as well as the size of the pits and lands, all right, for each and every type of data, or each and every type of disk that we talked about as well. All right, as you can see, the storage density that we have with our Blu-ray disk is by far greater than that of our CD as well as our DVD. Okay, so that is essentially the difference between a hard disk and the and optical media. It's worth mentioning that obviously when it comes to optical media, we have media that has gone through a number of different generations. The first generation being the CD, VCD, and the mini disc. Second generation, we're talking about DVD and the ultra density optical media. Third generation, Blu-ray, all right, and the HD DVD, all right. But now, as we go further, the next generation include discs that can actually store beyond a terabyte or more of data onto the same disk size. In fact, there is something that's known as the holographic versatile disk, which can store up to 6 terabytes worth of data. All right. And there are some who actually think that certain optical media can actually be the idea for long-term storage of the future, essentially. Okay, that basically concludes the topic of data storage. We are now going to take a look at the way that operating systems work, all right, especially in relation to memory management. We're also going to be looking at process management as well as I/O management. All right, so what does the operating system do, and what does the computer do in different areas? All right, so what do we mean by memory management? Nowadays, most of our computers are uniprogramming systems, all right, or rather, sorry, are multi-programming systems, which basically would require the computer to make up, or rather be able to execute more than one program or more than one process at any given point in time. All right. Essentially, what we need to do, all right, in order to allow our system, all right, to to carry out more than one process at any given point in time, is to give our operating system a memory management system in order to identify the individual processes that it is actually carrying out. All right, all right, these processes in memory, all right, in such a way that these processes do not affect one another. In fact, whenever we are creating a memory management system, essentially the memory manager itself is responsible for allocating space in memory for each and every, all right, so that they would be able to address it accordingly, all right, and point to the right locations within memory in order to be able to know which instruction they need to access, or know which memory areas they would need to access in order to obtain data, and so on and so forth. All right. They would also need to be responsible for deallocating memory. All right. It also needs to keep track of which parts of memory is free or which parts of memory is allocated, so that you do not overwrite. All right. Processes with yet other processes. All right. It also needs to know about the it also needs to keep track or maintain a maximum utilization of memory as possible in the most efficient way. All right, needs to not allow one process to interfere with another process. Essentially, you need to form some form of memory protection between processes. All right. Now, this memory management is usually handled partially in software and partially by hardware. All right. And when we're talking about the hardware component that takes care of this is known as the memory management unit, or MMU. Okay. Now, when we talk about memory management, all right, memory management can make use of what is known as different schemes. You have what is known as contiguous allocation, and you have what is known as non-contiguous allocation. What does that mean? When we say contiguous allocation, it means that the entire process, all right, is going to be stored in its entirety, all right, in memory, okay? That only parts of the process are going to be stored within memory, all right? Now, when it comes to contiguous allocation as well as non-contiguous allocation, you also have two different variants for each. All right. With contiguous allocation, we have what is known as fixed size partitioning and variable size partitioning. And when it comes to non-contiguous allocation, we have paging and demand paging. Let's first take a look at contiguous allocation and try to understand the differentiation between the fixed size partitioning and the variable size partitioning. So, with contiguous allocation, essentially what we're talking that each process is going to be stored in a continuous block of memory, which is known as a partition. What does that mean? It means that all of the instructions and all of the data that is required for that process to execute is going to be stored in one block in this relatively the same location within the partition. All right. Now each partition, all right, is going to be allocated to one process and one process only. All right. Each partition is also going to have what is known as a base, all right? Basically, the memory location or the address, all right, of where the start of the partition is going to be. It's going to have a limit, all right, which is basically the size of that particular partition, all right? And the operating system on its side is actually going to keep store of a partition table, which is which is essentially going to be keeping track, all right, of the base, the limits, and the states for each and every partition, all right, that happens to be in main memory. Essentially, you are going to identify the state is essentially going to identify whether or not that partition is free or not for another process to make use of, essentially. All right. So with fixed partitioning, essentially what what the system would be doing is it will be splitting up main memory, all right, into a number of partitions of fixed size. So you would be saying, listen, I have I don't know, just to give you a very rudimentary example. I have 4 gigs worth of memory, and I'm going to be splitting my memory into 5 equal parts, or 4 equal parts of half a gig each, for example. So each partition will have half a gig of space in order to store a particular process. I'm exaggerating on purpose so that you would be able to understand me. All right. So essentially, I would have 8 partitions of half a gig. All right, in order to make up that 4 gig space that I actually have. All right. Now, obviously, um, every computer, whenever you're running a computer, whenever you're going to be running a process, you're not going to be running a process in isolation. You're also going to be running the process over and above the operating system. So you're always going to have an element which is going to be reserved for the operating system. When we talked about fixed partitioning, we're talking about partitioning for the remaining amount of space. Okay? Is this clear?
Yes.
Okay. So essentially, what would happen is that once you split your your memory into these fixed size partitions, all right, you would allocate processes to these partitions. Now, the degree of which you're going to have multi-programming is going to be determined by the amount of partitions that you have. So if I only have 8 partitions, for example, then I can only run 8 processes at any given point in time. All right. If I have 12 partitions, I can run 12 processes at any given point in time, and so on and so forth. All right. So it's important to be able to create partitions, or numerous partitions, so that you would be able to have numerous processes running at any given point in time. But also you need to have partitions which are large enough for the types of processes that you want to try to run. Okay, so it's a sort of like a bit of a balancing act. So you need to make sure that your partition sizes are sufficiently large enough in order to accommodate your processes. If a process does not fit a particular partition size, then you essentially cannot run it on that particular machine. Okay? Now, essentially, whenever you're going to be placing a process within a particular partition, it is going to be the case that either your process fits in exactly into the partition that you actually have given it, or else, more frequently, it's actually going to be stored, or it's rather going to have some residual space. Essentially, it's kind of like saying, I have these boxes, all right. I'm going to give you a box for every book, for example. If your book is slightly smaller than the box, then you're going to have a residual space around it. That is essentially what we're going to be talking about with regards to fixed partitioning. With fixed partitioning, all right, the processes might not necessarily have the same size as the partition itself, and therefore you would get what is known as internal fragmentation, or wasted space within the partition itself. Okay, that is where variable size partitioning comes into play. All right, so instead of limiting yourself to the number of different processes that you might have, you would literally create partitions on the fly. So essentially, whenever you're going to open up a new process, it would request the amount of size of a partition that it would require, right? And essentially, the operating system's job is to find the hole, all right, within main memory that can be used for that particular process, and you will allocate it, all right. Obviously, um, uh, the uh, um, uh, the the process, once it has been terminated or has been released, the operating system will then need to amalgamate, all right, any neighboring free partitions together in order to create one big freer partition, so that any other processes that might be coming in at a later stage might be able to use up that slot. All right. Notice that a hole that is available for a particular process, again, might not be exactly the same size required for the process. It probably is going to be a bit larger, all right? So if your process requires, for lack of a better term, 10 megabytes, and you have 20 megabytes of a hole of free memory in your in main memory, in your RAM, then essentially what you would do is you would create another smaller hole of 10 megabytes later on, all right, which can be used for other processes, all right? But if we take a little bit of a look at this example, all right, so notice we have our main memory, all right, and we have our operating system running constantly in the background. Let's say that we have our first process, process 1, which is allocated in this space over here. Process 2 comes along and it's allocated this slot here. Process 3 comes along and it's allocated that slot there. Let's say process 1 terminates. Therefore, this block now becomes available. Process 4 comes along and takes or makes use of this area that was vacated by process 1. All right. Let's say that after process 4 comes in, process 2 terminates. Therefore, we have more space introduced over here. Let's say that process 1 comes back in, all right, and it's going to be making use of some space over here. And let's say that another process 5 comes in that is making use of some space over there. So notice what can happen after a number of allocations of processes and deallocation of processes. Essentially, after the number or a number of these allocations and deallocations happen, you're going to come up with what is known as external fragmentation. Essentially, what that means is that you might have a situation whereby you would need to place another process within main memory. Technically speaking, the amount of free space collectively, all right, would be enough for that process in order to be placed within main memory. However, all right, the contiguous part of free memory that is available, all right, is actually smaller than the process that you need to have. Let's take, for instance, this case, all right, where you need to place a 65 or 68K block for a process, all right, in this memory. So notice over here we have this light blue color, all right. Those are your free and empty spaces, all right. Notice that if you had to add all of these together, all right, you would know that we actually have more than enough space in order to add this new block. However, next to each other, they are not. All right, so you have what is known as external fragmentation. Essentially, what needs to happen is that at some point, your operating system needs to go through a process known as compaction, whereby it would literally compact all of the active processes into sort of like a contiguous part, and all of the free available space into an uncontiguous part, and therefore you would be able to allocate your new processes. However, notice that this process of compaction is actually a process that takes up a lot of resources. It's quite an expensive process. All right. Think about it in this way. If you are trying to clear your desk, you're probably going to need a lot more space than the desk itself. All right. Why? Because when you are clearing things around, you would need to literally move things into temporary locations. All right. In order to make space for yet other objects. Essentially, if you had to think about it, it's basically defragmentation. All right. Of your main memory. All right. So essentially, you would need to do it from time to time, but it's an expensive process. Okay. Is this clear, guys?
Clear on
Eva.
mind. Thank you.
Okay. So this is another example of compaction. All right, that can actually try to maximize the amount of free contiguous space with each other. All right. Now, there are a number of different strategies that one might use in order to try to limit the amount of times that you would need to perform this process. All right. One might use, all right, a strategy such as the first fit approach, where essentially you would place a process in the first available location, all right, which would actually fit that particular process. All right. Another approach would be the best fit. So you would look through each and every one of the holes that you have within memory, and you would select the smallest one, all right, which is just big enough for the process that you're trying to introduce. All right. Essentially, this would require you to actually search through the entire table, all right, unless it's already sorted in some way, and then place that process into that particular hole, all right. But however, this would actually create a very small internal fragmentation, or sorry, external fragmentation element within main memory as well. Another approach would be to use the worst fit. So essentially, you would look for the largest hole rather than the smallest one, which would basically also require you to search the entire partition table. However, the hole that is left behind would be large enough, hopefully, in order to add yet another process. Notice that each and every one of these strategies has their pros and their cons. However, none of them solve the fragmentation problem. All right. So that was essentially the idea behind contiguous paging, our contiguous memory allocation. One thing that I wanted to point out is that whenever we have memory locations, all right, within processes, all right, we tend to make a differentiation between a physical address and a logical address. A physical address is essentially the address in which that particular piece of data, all right, or that particular instruction happens to reside in your RAM, all right? So the actual physical address, all right? The logical address, all right, is essentially the address that is probably used by the application underneath, okay? So let's take a bit of an example, all right? So whenever you would have an instruction, jump to memory location 1000, in reality, that location 1000 is not a physical address, but rather it is a logical address in relation to the start of that particular program or that particular process. Therefore, it is a logical address. Therefore, whenever you're running an application, all right, say for instance, you're running your program, all right, and your program's partition base starts at memory address 5,000, for example. When it comes across that that instruction to jump to memory location 1000, in reality, underneath, that is translated to jump to memory location 6000. Notice that this jump to memory location 1000, that would be your logical address, and that would be converted back into your physical address. Notice this is why it is actually possible to compact, all right, your processes, all right, without really and truly affecting your application, all right, because essentially what you're doing is you're just changing around the base address, all right, of each and every process, therefore shifting everything upwards, all right. Therefore, underneath to the program itself, it does not necessarily need to change its logic as to how it's actually written. That is actually handled by converting the logical address into a physical one. All right. Now, the way that this is done, all right, is by mapping it using what is known as the memory management unit, all right, or the MMU, all right. Essentially, what we are talking about is that that when we are writing applications, all right, and when we're writing code, we're really and truly working with logical addresses, which are in turn mapped, all right, to a physical address that happens to be on our main memory. Okay. So essentially, in order to be able to dynamically change a logical address into a physical one, all right, all of the addresses, all right, that are being requested by the CPU would pass through the memory management unit, all right, which would dynamically convert them into a physical address, being able to access the correct data location for that particular request. Okay, how is this done? So essentially, the CPU will send its logical address, all right, to the memory management unit. Now, the memory management unit would require, all right, to know the base for that particular process as well as the limit for that particular process. In fact, the memory management unit stores the base for that particular process and the limit for that particular process within what is known as the base and limit registers. All right, these are loaded in by what is known as the dispatcher. All right, essentially, all right, if the limit, or rather, if the local logical address that is provided by the CPU is greater than the limit value, all right, meaning that we're trying to access a location outside of the region, all right, of that particular process, what happens is that you would get a memory violation, all right, where essentially you would get a bus error, all right, back to the CPU. However, if the address that you are trying to access is smaller or equal to the limit, all right, then what you would do is you would take that limit, or rather take that address, add the base to it, and that would give you the physical address, and you would be able to access that in main memory. So essentially, this is what happens. So your CPU passes in a logical address into your memory management unit. All right. The logical address is compared to the limit register, or the value within the limit register. If the logical address, all right, is greater than the limit address, all right, it will go into this, what is known as the trap memory violation, all right, which is essentially going to be relayed back to the CPU. Otherwise, all right, if the logical address is actually smaller than the limit address, all right, then you would take the logical address, add it with the base register, and that will provide you with your physical address. Is this clear, guys?
Not really.
Not really.
I'm kind of. I'm trying to. I'm thinking of the memory read cycle. That's why from the CPU, I'm trying to marry these concepts.
So essentially, you would agree with me that when you are writing an application, all right? Imagine you're a programmer, okay? When you're writing a program, all right, are you going to know what the user of that application is going to be running in conjunction with that program?
No.
No. So the idea of logical addresses versus physical addresses becomes more pertinent. So essentially, whenever you're trying to tell your application or your program, listen, I would like you to access this particular memory location, in reality, you're not telling it to access that physical location, but rather a logical location. All right. Okay, so essentially, what we're telling it is, if we're going to be starting at memory location 5000, for example, all right, then the memory address that I'm trying to tell you to access is going to be in reference to that location that I'm going to start with. You understand?
Not really.
Okay, Mano. Let me give you an example. So, if I Mano, if I tell you, all right, to move 5 paces forward, okay, the destination that you're going to achieve when you move 5 paces forward depends entirely upon where you're starting from, correct?
Yep.
All right, so essentially, if I'm telling you to move 5 paces forward in a field, all right, that's one thing. All right, if I'm telling you to do it in on a busy high street, that's a different thing. You know, people, the location where you're going to end up is going to be completely different.
Well, that's why logical and physical.
Yes, exactly. So essentially, the physical space that you're actually going to achieve, all right, is going to be dependent upon where you start, okay, or where your process is actually housed. All right, in this case, okay. That is essentially what we're talking about. So essentially, every program is going to have all of its instructions, all right, placed somewhere in memory, all right, in a block of in a block in memory. Okay. Now that block is going to start somewhere. All right. So essentially, what we're doing is, instead of telling our program, listen, you need to physically access memory location 1000. All right. What we're really saying is we want to access memory location 1000 in relation to the starting position of our. That's what we're saying. All right. That's the difference between the logical address and the physical address. Okay.
Okay, so would the instruction vary depending on
No, the instruction does not vary. No. In fact, this process of how the address, all right, is converted from a logical to a physical one is literally hidden away from the CPU. The CPU is not aware of this. Okay.
okay.
So the CPU is reading these instructions. All right. The instruction is telling it, listen, jump to memory location 1000, for example. But the memory address unit or memory management unit, sorry, is actually going to take that logical address that is going to be given by the CPU. All right. And is going to convert it into a physical address in order to obtain the correct location. Do you understand?
Yes, much better now. Thank you.
Okay. Now, essentially, the way that it does this is that it takes in the data about the particular process that is actually being executed. Essentially, every process has what is known as a base, essentially where you're starting from, and a size or a limit. Okay, so if we're going to start off with the assumption that, listen, every process can only operate, all right, within the limit of that particular process. It cannot access any other memory locations outside of that limit. Okay? If that is the case, then we're doing something incorrectly. We're trying to violate something, all right? And that's when we would notify the CPU. Oi, we're doing something incorrect here. Okay? So that is why we are comparing the logical address with the limit. So essentially, if our logical address is bigger than the limit, or the size of my of the process block, then that means that we're going to try to access some space outside of that particular process location. All right. If it isn't, all right, so if our logical address is actually smaller than our limit address, then essentially what we would need to do in order to obtain our physical address is we'll take our logical address and add it to the base address, and therefore you would get your physical address. Is that clear?
Yeah, so the base register then is kind of varies. That's
what's going to vary.
That's the starting point. All right, okay.
That's your starting point. The limit is essentially the size. Okay?
That's all.
Okay, so that is essentially the idea behind the contiguous approach to memory management. Another approach is to use what is known as non-contiguous memory management. This involves a technique known as paging. So, paging is essentially a scheme whereby whereby we remove the requirement for processes to be stored in contiguous memory chunks, all right, altogether. Essentially, what you would do is each process would be given, all right, a number of pages, all right, to store the data that it needs to store. Okay. The cool thing behind paging is that it also allows for one to retrieve data, okay, or retrieve pages for a particular process from secondary storage, such as a hard disk, all right, to be used in conjunction, all right, with the main memory. Essentially, the idea of virtual memory, all right, essentially memory that doesn't really exist within main memory but exists within a virtual space, essentially. Okay, in fact, this kind of memory management is by far the more popular approach that is being used nowadays within modern operating systems. So let's try to understand what this is all about. So essentially, what what you would do is you would take your main memory space and you would divide it into equally sized blocks known as frames, similar in idea to the fixed partitioning approach. However, in this case, you are going to create a number of frames. It doesn't matter if they're very very small, but they're going to be smaller than the fixed partitioning frames. So essentially, they're going to be blocks, all right, which are equally sized, all right, known as frames. Notice that the frame sizes are invariably they invariably have a size which is always a value which is to the power of 2. All right. So essentially, all right, if you have a frame, all right, the block size is going to be 512, 256, 128. All right. There are going to be values which are to the power of 2. All right. So a typical frame might be 512 bytes, which is 2 to the power of 9, or 16 kilobytes, which is 2 to the power of 14. All right. Some systems nowadays can actually have frames as large as 4 megabytes, which is 2 to the power of 22. All right. But notice there are always a value to the power of 2. All right. The frame in itself is the smallest allocatable unit of memory for a at any given point in time. So essentially, a process, all right, would need to make use of a number of frames at any given point in time. So you're going to have a number of frames which are occupied and a number of frames which are unoccupied. And essentially, the operating system would need to maintain a table of your frames, all right, which would indicate whether or not that particular frame is free or allocated to some process. It will also need to have some form of ID in order to be able to reference that particular frame, all right, and it also needs to have some other information such as whether which is essentially going to be information that's going to be used by your MMU or your memory manager, all right, in order to be able to address which process belongs to which frame, essentially. Okay. So that is how your main memory is going to be split up. On the other hand, your processes, all right, are going to be split up into equally sized pages. All right. Now notice, each page is going to be equal in size to each frame. So as you can imagine, all right, it could be that a particular process would need 4 frames, for example. Another process might need 6. Another process might need 32. All right. Another process might need 3. All right. And so on and so forth. It all depending on how big that particular process is. Notice, all right, that it could be that the process does not take up the entirety of the amount of pages that it uses. All right. So when I say a process takes up 4 pages, it could be that in reality it could have done with 3.5 pages. All right. But that additional half a page cannot actually be used for anything else. All right. It's used for this particular process. That's about it. Okay. So the fact that you have pages and frames of the same size, that would mean that now you can allocate a page into a frame, all right? And essentially, you can swap around these pages within these frames by means of what is known as a frame table. Essentially, a frame table and a page table are going to be constructed, all right, in order to identify, all right, which pages are in the frame, are in the frames, all right, which frames are allocated, which frames are not allocated, and so on and so forth. All right. And in this way, all right, the process page table would record which frames are, which frame each page is actually placed And the frame table, on the other hand, is going to indicate which frames are allocated and which are not, essentially. So, essentially, if we have a process, let's say a process is made up of 4 pages, all right, you would then need a page table, all right, in order to identify which page is stored in which frame. So in this case, page 0 of this process is stored in frame 3, which can be seen over here. Page 1 of this process is stored in frame 0. Page 2 of this process is stored in frame 9, and page 3 of this process is stored in frame 7. So you'd have literally a process table for each process, essentially. Okay? Now, you can also have what is known as page and offset addressing. Let's assume, for argument's sake and for convenience sake, all right, because we work predominantly with decimal numbers rather than binary, all right, that each page, all right, has a size of 1000. Okay, so we're saying that page 0 is going to contain logical addresses from 0 to 999. All right, page 1 is going to contain pages from 1000 to 1999. All right, page 2 is going to have values between 2000 and 2099, 999, and so on and so forth. Okay, so those are essentially the way that these logical addresses are actually going to be divided. All right. Now, essentially, yes.
If we modify the page, because I know you can, I've done it before, and I know the effects. It makes a difference if you have an SSD, but I can't figure out why it's better off to have less sometimes paging or page memory than more. How does it affect the processes?
The reason why it's sometimes a good idea to actually have smaller pages than larger ones is that, as we're going to be coming to it, that the amount of waste that you would have with each page would then grow the bigger the page becomes. Okay, so that's one thing. Second thing is that when it comes to virtual memory, all right, the bigger the page becomes, the more time it's actually going to take in order to swap in and swap out pages from secondary storage into main memory. It takes longer.
But if you have an SSD, then it takes a bit less time to replace the page memory.
True,
and so you get the advantage of a bigger page, and you pay.
True, but then an SSD also has a limited number of read and writes.
Yeah. Yes, it has.
So it becomes a bit problematic in that case, so it's a bit of a give and take situation.
Yeah, it depends on what you want from it, maybe, as well.
Exactly. All right. Anyway, what I was trying to come across is that essentially, in order to be able to locate the memory location in a quicker way, all right, and be able to identify whether or not the address that you're trying to access, all right, the logical address that you're trying to access is within one page or another page or another page or another page, instead of actually having to go through each and every one of them, is that you would perform a bit of mathematical wizardry in order to help us out. Essentially, what we would use is we would use the quotient, or essentially the division, all right, between the memory address that you would require versus the size in order to determine which page you are actually going to access. And the remainder process would determine how far off from the start of that page you are trying to access that memory location. So let me give a bit of an example of what I'm on about. So let's say, for instance, that we are trying to locate memory address 2564. All right. If we take 2564 and divide it by 1,000, all right, that is going to give us 2 point something. All right. Essentially, when we're talking about the quotient, really and truly, what we're talking about is the number of times 1,000 goes into the value 2,564. So essentially, that goes into it 2 times. All right. However, the offset is actually going to be the remainder of the value. If you had to take 2,564 and divide it by 1,000, what is going to be the remainder? The remainder is going to be 564. So essentially, what that means is that the page that we would really require access, all right, is going to be whatever the logical address happens to be divided by the size, all right? And the location within that page that we would require to access is going to be determined by the offset, which is going to be the logical address itself, modded, all right? So the remainder of the page size that we're trying to access. Now, the clever thing about having page sizes which are to the power of 2, all right, means that it would simplify the amount of binary division, all right? So let's say that we have a page size which is 2 to the power of n, all right? Then the offset essentially that we're going to need to calculate, or a mod p, all right, a being the logical address and p being the size of our page, is going to be the least n significant bits of the address a. So if this is our address here, all right, this entire address is over here, is the physical, or sorry, is the logical address that we're trying to access, and our page size is, say, of size 2 to the power of 14, then the least significant 14 bits is going to determine the offset. The other bits, that's going to determine the page number, which makes it a lot easier in order to pinpoint exactly where it is. Does this make sense? Did you understand this idea?
Still reading the slide. So and so.
So and so. Let me give you a bit of an example. So our CPU is going to try to access a logical address. As we know, a logical address needs to be mapped onto a physical one, correct?
Mm-hmm.
And now we're using paging in this case, so we're no longer using the contiguous memory allocation. We're using non-contiguous memory allocation. We know that it could be that our pages are going to be stored in various different frames within our main memory, all right, as we've seen here, all right? So page 0 is stored in frame 3, frame 1 is stored in frame 0, page 2 is stored in frame 9, and page 3 is stored in frame 7. So they can literally be all over the place. Okay? So far, so good. So, yes?
All right, I can segue.
All right. So essentially, what we need to do is we need to be able to identify which page we're actually trying to access. So we'll take our logical address, all right? And we know that our logical address is equal to our page multiplied by our page size plus our offset, essentially, okay? Notice that in our case over here, all right, 2,564 is equal to 2 times our page size, which was 1,000, all right, plus our offset being 564.
Which is the remainder.
Which is the remainder, which is basically what we're doing over here.
Mhm.
So how are we going to obtain this P? So we take this logical address and we divide it by our page size. Once we divide it by our page size, we find our page P. We take that and look for it within our process table and say, all right, our page P is being stored in frame F. So that is where we're actually going to be looking for it within our main memory. All right. Our offset is then calculated by the remainder. All right. And once we've calculated the offset, we copy that offset and place it here. So essentially now our physical address is going to be the frame location, all right, multiplied by a page size plus the offset. So therefore, we'll find frame F, okay, and we'll go off by the offset, which was determined, all right, in order to find the memory location that we're trying to access. Is this clear, guys?
Well, here, better, thanks.
Okay. Everybody else?
Okay, sir. Thanks.
It's okay. Thank you.
All right. So, this is again the same example being done numerically. So, assuming again a page size of 10,000, all right, and the CPU wants to jump to memory location 2,564, all right. So, we'll pass 2,564 as our logical address. By dividing this number by our page size, we would get which page we're actually talking about. In this case, we're talking about page 2, which is stored in frame number 9. All right. We have our remainder, all right, which is 564, which is going to be carried over here to our physical address. So essentially, the physical address that we're trying to access is 9,564. 9,564 will be over here, okay, in this offset over here within physical memory, and then you'll be able to retrieve that data. Essentially, that's what this is all about. Okay, so essentially, this is a general idea of how paging works. Right, this is a worked example, essentially. Okay. Now, as I mentioned, all right, with this idea of paging, the bigger the size is for your page, the more internal fragmentation you can actually get for each page. All right. However, on the other hand, all right, if you have pages which are smaller in size, then that means that you're going to have much larger page tables, all right, that you need to keep track of in in your operating system. So comme ci, comme ça, depends entirely on your implementation and how you want to actually operate when it comes to these applications. All right. Another process that we need to talk about is the idea of demand paging. Essentially, one thing that paging allows us to do is that it allows us to place only those pages that are required in main memory at any given point in time. So that means that a process does not need to have all of its pages loaded up in main memory at any given point in time. All right. This also leads to the locality principle. If you remember, we talked about this idea when we were talking about caching. All right. Remember the idea between temporal and spatial locality principles. All right. Essentially, the idea behind the demand paging is that we are allowed to load in, all right, pages that we are not using, that we weren't using at any given point in time, back into main memory, all right, through the use of virtual memory. As we sort of hinted at earlier, virtual memory is where certain pages are actually stored on the hard disk. So, what is the advantage of having demand paging? Well, the major advantage is that the pages that are needed are loaded into main memory, which means that you're going to reduce your load times because you're not loading every single page into main memory. All right. This means that you can add more processes. All right. And you can work on more processes, and therefore you're maximizing the utility of your operating system. All right. You would have less latency when you're starting up programs. All right. And you do not necessarily need additional hardware in order to make paging exist. However, um, uh, as like with anything, you also have your disadvantages, where it means that essentially it could be the case that individual programs would have extra latency when they are trying to access a page for the very first time, because obviously you would need to load that back up from your hard disk. And it also could be the case that depending on which replacement algorithms you might have, you might be swapping pages to and from your hard disk, which would slow things down, and it might also make things and the might make your replacement policies a bit more complex. All right. So, what is virtual memory? So, virtual memory is essentially a portion of your hard disk, which is used in order to store pages that are not really being used at that current point in time. In fact, virtual memory allows you to increase the amount of multiprogramming that your computer can do. All right. But although virtual memory is not directly accessible by the CPU, all right, it can it can offset, all right, the contents of the process that are not currently required in main memory at that particular point in time. So essentially, what you would have is you would have a number of frames in main memory, and you would have a number of frames, all right, which are stored as swap files within your hard disk. All right. Essentially, your process table would now include also not only the relation between whether or the page number to the frame number, but it will also include a valid bit. All right. Essentially, the valid bit determines whether or not that particular frame is within main memory, or whether that particular frame is stored in your hard disk. All right. So in this case, frame 12, all right, which is literally storing page 1, is invalid because it is stored within the swap file within your hard disk. Essentially, if you need to read this, then this page 1, all right, would need to be swapped into your main memory so that you will be able to access it at a future stage. All right. So that is essentially the idea behind it. In fact, this process of taking a swap file and placing it back into main memory is known as swapping in. All right. This is generated whenever there is this page fault. All right. So essentially, whenever you have an instruction that is referring to a memory location which is understood to be within virtual memory, the memory management unit will detect it, all right, via the validity bit. It will cause this page fault, and it would page in, all right, this required page into main memory to be able to access it later on. All right. So essentially, this is the process that goes in. So essentially, you would have an instruction such as jump to memory location 1000. You would reference it, and you would notice that it is an invalid page, which means that it is on your disk. All right. That would cause a trap, all right, which is notifying your operating system, in which case your operating system will retrieve it from your hard disk. That hard disk, that page would be retrieved from your hard disk and placed into a free frame within your physical memory. All right. It would then update your process table, and then you would restart the instruction so that you now would be able to access the physical memory itself. Okay. Now, obviously, the way that pages are replaced or swapped in and swapped out depends entirely upon what is known as a page replacement policy. Essentially, the page replacement policy is a strategy which determines how pages are actually going to be swapped in and swapped out, all right, depending on this particular strategy. All right, a typical strategy that might be used would be the least recently used or the least frequently used, for example. Obviously, these policies, all right, would require the hardware to maintain access to certain statistics as to how often you're actually accessing that particular memory location, all right, um, uh, or when was the last time you accessed that particular memory location, therefore being able to maintain an ideology as to when those memory locations were actually used. Okay, but you could also have a situation whereby you would have a process which is constantly swapping in and swapping out pages, all right, which in turn slows down the system. This is known as trashing. Okay, essentially, this is where your system starts to slow down quite considerably, because remember, your hard disk, even if you're running on a solid state drive, those run at a much slower speed than your CPU. Therefore, the only cure for that is to reduce the amount of multi-programming that you have on your system. Essentially, close as many processes as you can in order to avoid trashing, or else stop your long-term scheduler, which is essentially the scheduler that is going to determine which processes are going to be included into your into your execution cycle. All right, that will slow down the amount of new processes that are sort of like admitted into the need for being executed, essentially. All right, so you need to keep that in mind. Notice also that when we talk about multi-core processes, all right, or multi-threaded processes, all right, it is a situation whereby you have um, um, multiple execution lines working on the same process at the same time. All right, if you have multiple multi-cored CPUs, it can possibly mean that you have two CPUs or two cores on the CPU working on the same process at any given point in time. All right. This means that essentially these threads, all right, are going to be accessing the same memory locations, all right, since they are working on the same processes. The way that this is actually handled, all right, is by the use of what is known as a time division multiplexing, all right, which essentially is going to allow these threads to have shared resources, all right, without actually overlapping with each other. Essentially, you would have a portion of the main memory which is actually going to be shared between both threads. However, you would need to keep track of the execution state of each thread on what is known as a stack. Essentially, a stack is basically a memory structure that is going to identify the way that or the current state of that particular line of execution. All right. However, they're going to have access, all right, to the same memory objects on what is known as a heap. Essentially, the heap is going to be in common, all right, for each thread, all right. However, each thread is going to have its own stack in order to reduce, all right, the possibility of having threads screwing up, all right, the data of objects within within main memory. Okay, so that is something about memory management. Let's talk a little bit about I/O management. So essentially, we know that every computer makes use of a number of peripherals, meaning a number of I/O devices, such as keyboard, mouse, microphone, you name it. All right. All of these different types of devices are known as I/O devices, and they run at different speeds, and they also have different limitations. All right. Now, every time we talk about an I/O operation, we're talking about four main types of operation. You have a control operation, which is essentially an operation where you're going to instruct the device in order to do something. All right. You have a test operation, which is essentially going to be able to check the status of that particular device. You're going to have a read operation, all right, which is going to read data from that device, and you're going to have a write operation, which is going to allow you to write data from to that device. Now, obviously, different types of devices are going to have different types of operations that they are going to handle. So, for example, the mouse, for example, is not going to have a write operation because you're not going to write anything to the mouse. You're just going to be reading from the mouse. And similarly, you might not be reading from a printer if it's just a printer. So it depends entirely on the device that we're actually talking about. Okay. Now, every I/O device, all right, is going to be connected with the computer via the system bus, but they're going to be connected to the system bus via a module on the device itself, known as the I/O module. Essentially, the I/O module is serving as a go-between, as an interface, if you will, between the CPU itself, all right, and the device, all right. Specifically, what it does is it accepts commands from the CPU, all right, and provides a buffer between the computer and the device in order to be able to send data or receive data more efficiently, and it also performs data conversions, all right, from what the CPU understands to what the device understands. So essentially, the if we're talking about a printer, all right, and if we're talking about an inkjet printer, the CPU might say, "Listen, I want you to print out this particular dot of ink in this particular location," and the device would say, "All right, I need to move the ink head by so much in this location in order to drop this particular ink droplet onto the piece of paper." Essentially, all right. So it acts as an interface between the CPU and the device itself. So essentially, all right, you wouldn't actually need to know how the device underneath operates really and truly. Okay. So essentially, every device, all right, every peripheral is going to have its own I/O module, and they're going to be communicating with the CPU via the bus. All right. Okay. So, how can we actually address I/O devices? Well, there are two ways that one can actually do this. What you could do is you could assign each I/O module a port or a register, essentially. Now, the I/O module would have three sort of like registers. It would have a data port, right, a status port, and a control port. All right. Essentially, the data port is going to be the port with which it's going to read, or the status port is actually going to store the status of the particular device so that the CPU will be able to check whether or not that device is ready to send data or to read data or whatever. And you have the control port, which is going to be the port in which the CPU is actually going to send commands to the device so that it will actually be able to execute them on its own. Now, each I/O port is going to have a unique address that is going to identify it. Okay, so if we had to blow up the I/O module, essentially you're going to have your data registers, your status and control registers, and your control logic. Your data registers is going to be reading data from your data bus or reading and writing data to and from your data bus. Your status register is going to be reading and writing data to and from your data bus as well. All right. Your control logic is going to be taking your address bus data and your control bus data, and depending on what, and is actually going to be writing to and from these data registers and the status control registers in order to communicate via the system bus. Notice that on the other hand, these devices or these registers and these modules are also in communication with the I/O device itself. All right. Now, the I/O devices have some form of address space. All right. So essentially, what you could do within a CPU, within a computer system, is you could say, "Listen, I am going to have a separate addressable space for I/O." All right. So, for example, you can say, "Listen, I'm going to have 8 bits reserved for I/O addressing," which basically means you're going to have addressing capable of registering 256 different I/O devices. All right. In such a case, the CPU would need to have special kinds of instructions which would allow it to read from I/O ports whenever it needs to read from an I/O or write to an I/O device. All right. There are a specific set of Intel CPUs which actually do this through the use of in and out instructions. So essentially, in would be meaning that you're reading from an input device, all right? And out means that you're going to be writing to an output device, essentially. Okay? However, you could also map I/O devices through what is known as memory mapped I/O. Essentially, to the CPU, what you're going to be doing is you're going to be giving your I/O locations as though they were literally addresses that you have for main memory. So essentially, you're going to be using the computers or the CPU's address space, all right, in order to map I/O devices. So essentially, for the CPU, it's not really going to make much of a difference whether or not you're going to be accessing main memory or whether you're going to be accessing an I/O port. So, for example, you could have memory address 4000 mapped to the input port of a keyboard and 4001 mapped to a keyboard mapped to a printer, for example, and so on and so forth. But to the CPU, it thinks that it is accessing main memory, really and truly. So that is one way of going about it as well. All right. Now, it's also worth mentioning that I/O devices in general are by far slower than your CPU counterparts. All right. Essentially, all right. What you don't want to have happen is that you don't want your CPU to sort of like wait around for your I/O device to become ready in order to send data or to receive data, etc., etc., etc. So what do you do? In order to combat this, you would use the idea of buffering. Essentially, you would have a device which is ready to, which would have a buffer, all right, in order to be able to allow the CPU to write to the buffer, all right, whilst it's reading from a different section of the buffer. In fact, what you could do is you could have multiple layers of buffering. So you could have your CPU, for example, writing to different levels of the buffer, whilst the I/O device is reading from another. All right. This is in order to increase the speed by which these devices would actually communicate with each other. And different devices have different names for this. So, for example, a printer would have what is known as a spooler. A hard drive would have what is known as a cache, and so on and so forth. All right. The idea, again, is in order to speed up the communication process between them. All right. It's also worth understanding that whenever you are going to communicate with a particular I/O device, you would actually need to have what is known as handshaking happen between the computer and the device before the transfer of data actually can happen. It's kind of like the three-way handshake that we sort of like discussed last week with regards to the IP three-way handshake. But essentially, the idea is similar. So essentially, the computer or the CPU will send a signal, a control signal to the device. It waits for an acknowledgement. All right. If the acknowledgement arrives within a certain amount of time, then therefore data transfer can actually happen. However, if the acknowledgement does not come back to the CPU after a certain amount of time, essentially that acknowledgement has become timed out, and that would basically mean that that I/O device is not going to be accessible. Okay. Now, in order to be able to have devices communicate with your CPU, you could use different I/O architectures. All right, we're going to go in order from simplest to most complex. The simplest architecture is going to be the worst performer. All right, the best and most complex architecture is going to be the best performer. All right, these are the programmed IO or your CPU is constantly checking the status of each and every IO device to see whether or not they are ready to receive another word when you're actually writing data to that device, or when reading, it will see whether or not that device is ready to deliver yet a new other word. So imagine having the CPU, all right, which imagine again is a lot faster than these other devices, saying, "Are you ready? Are 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 you ready?" Notice that this could actually eat up a lot of CPU cycles because the CPU is constantly waiting for these devices in order to be able to be ready in order to read or write to. Okay. So what can happen in order to this? Well, you might want to make use of buffers in order to help this out. All right. Another approach is the idea of interrupt-driven I/O. Essentially, the I/O device is going to send an interrupt signal to the CPU and tell it, "Listen, you need to to notice me. Essentially, you need to service me." All right. So, for example, if you're going to be typing something on your keyboard, when you press a key on your keyboard, that sends a signal to the CPU, and the CPU will say, "Okay, I'm going to stop whatever I'm doing. I'm going to take the signal that is coming in. I'm going to process it, and then I'm going to continue from where I left off." All right. Essentially, that is the idea. All right. But notice you can actually have a situation whereby you have multiple devices which are producing these interrupts. So what happens? So first, you would have a device that would trigger an interrupt. All right. So let's say device 3 triggers an interrupt. All right, and goes to the CPU. The CPU says, "All right, let me finish the current instruction that I am working with." All right. Once it finishes that current instruction, it says, "Okay, let's see which of devices has actually caused the interrupt." So it would cause the first interrupt handler. All right. The first interrupt handler will now sort of start polling the different interrupt handlers which exist for each device that you have. All right. It will figure out that it is the third interrupt handler because it was the third device that actually caused the interrupt. That is returned to the first interrupt handler. That in turn informs the CPU, "Listen, that this is device number 3 that requires the servicing." All right. The CPU will service that device, and then it would continue execution with its next instruction. That is essentially the process that is going on within interrupt-driven I/O. Now, another sort of like more improved version of this interrupt-driven I/O is the use of vectored interrupts. What do we mean by vectored interrupts? Essentially, what we're saying is that in order to reduce the need for having your first level interrupt handler to pull through all of your different I/O devices, what you could do is you could give each interrupt what is known as a vector number, an interrupt vector number. Essentially, this interrupt vector number is going to be an index that is referring to the interrupt vector table. All right. So it essentially uses that value in order to find which device it actually needs to handle. It also can be used as a form of what shall we call it? We call it a form of priority, essentially. So a device with vector interrupt 0, for example, would have a higher priority than something with a vector interrupt 7, for example. Okay, so let's take another example. Let's say that we have device number 1, device number 2, device number 3. All right, and let's say that device number 3 is going to trigger an interrupt. Okay. So your CPU will finish the current instruction. All right. It will then send an acknowledgement back. All right. To the devices. All right. Notice that once it sends an acknowledgement back, it will pass through each device until it reaches the device that actually caused the interrupt. In this case, it is device 3. So device 3 will send back, listen, I was the one that interrupted you. All right. In which case, the CPU would look for the interrupt handler number 3 in this case, because this is device number 3. All right. It would service whatever the device needs to have serviced. Once that is done, it will tell the CPU, listen, it has been serviced, so you can resume back what you were executing previously, and then it will continue executing the next instruction. That is a more advanced version of the interrupt-driven I/O architecture. All right. So the cool thing behind this is that you can have what are known as multiple interrupt lines. Essentially, you can have them in different levels of priority. Say, interrupt line 0 would be the highest priority. Interrupt level 7 would be the lowest priority, and therefore what you would do is you would place fast devices on a higher priority line and slower devices on lower one. All right. If 2 interrupts go up simultaneously, all right, 2 or more go up simultaneously, the one with the higher priority is serviced first. All right. If other interrupts come in of a lower priority, those are ignored for the time being until this interrupt has been serviced. All right. Unless some form of higher interrupt comes into the mix. If 2 interrupts of the same priority go up at the same time, then essentially what the computer will do, it will service them in a sequential manner. It will first do one and then it will do the other, essentially. That is essentially how interrupt could also include priorities. The final form of interrupt I/O addressing is the form of direct memory access. Sometimes you have devices, such as, for example, your GPU or your hard disk, all right, which can be running at very, 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 very high speeds, which would flood your CPU if it had to work with interrupts for each and every byte of data that it actually needs to send to and from main memory. All right. So in order to not flood the CPU with all of these different interrupts, all right, what you would do is you would send one interrupt, all right, in order to tell the CPU that you need to actually send a block of data rather than a byte of data to main memory or vice versa. All right. In which case, the CPU would give you control. All right, of the system bus. In which case, the I/O module will be able to communicate directly with main memory without the interjection of the CPU. Essentially, without direct memory access, if a disk would need to write some data to main memory, all right, your disk will first need to communicate it with your CPU, and then your CPU will need to place that data into main memory, which obviously is going to slow down the process. All right, with direct memory access, all right, your disk will have direct memory access, as the name implies, all right, via the system bus after informing the CPU that a block of memory needs to be accessed or written to. All right. Now, direct memory access can operate in one of 2 ways. It can use what is known as burst mode, in which case the CPU itself is prevented from using the system bus as this process is happening, or else, all right, the device itself will steal CPU cycles, all right, known as cycle stealing, when the CPU is not making use of the system bus at that particular point in time, which might slow down the process. All right, so give one, or like they both have their advantages and their disadvantages. Okay, obviously, all of these I/O devices would work well together because they make use of these variables, which are controlled with what are known as semaphores. A semaphore is essentially a variable, all right, that can have a value. All right, now there are different types of semaphores. You have a binary semaphore and a counting semaphore. A semaphore which is binary can take two values, all right, 1 or 0, all right, which is used in order to acquire locks. So essentially, if you're talking about direct memory access and you want to have a lock on the system bus, you would have a binary semaphore within your I/O device. All right, 1 meaning that you have access to your to your system bus, 0 meaning that you don't have access to the system bus. Or you could also have what is known as a counting semaphore, which is essentially a variable that is going to record the initial number of resources available. All right, and each time a process starts to use a particular resource, it is incremented by 1 every time a particular resource is released. Then you would decrement it. This counting semaphore will essentially allow you to make sure that you're actually making use of all of the I/O devices in in a correct way. Essentially, as long as the count, all right, of this particular semaphore is greater than 0, then essentially access can be granted. All right. If not, all right, then essentially access is denied. That is essentially what I had to say with regards to memory management and I/O management. The one thing that I wanted you to sort of go over a little bit on your own, all right, guys, is the idea behind process management. All right. Essentially, we've talked about the idea of processes. Now, remember, a process is essentially the actual execution of programs. So do not confuse the two. A computer program is essentially a set of instructions, whereas a process is the actual execution of that program. All right, and as we've seen, an operating system can run multiple processes at the same time. Okay, so essentially, all right, when we're talking about a process, all right, what we're really talking about is the state, all right, of the code, all right, that has been written in a computer program, all right. So essentially, it's keeping track of which code has actually been executed, the process-specific data, where you're in within the line of execution, what is being stored within the heap, all right, the security attribute, so essentially knowing who owns this particular process and who owns the processor state, all right. So essentially understanding the value of the registers and the physical memory addressing, etc., etc., etc. All right. However, a process lives in one of 5 different states along its lifetime. All right. Initially, every process is going to be new. All right. Whenever you start up a process, it's going to be new. It can be running, all right, i.e., it's actually executing in the CPU. It can be ready, all right, meaning that it is waiting for the CPU to give it a time slice in order to execute. It can be waiting, meaning that it's waiting for some form of event in order for it to continue executing, or it can be terminated, all right, meaning that it has finished executing. Essentially, this is the state transition diagram that every process goes through. So you go from new to ready, all right, from ready to running and back to ready sometimes, or else you can go into the waiting state if you're waiting for a particular event. However, at some point, every running device will terminate, ideally. Okay, that's the idea. All right. Now, the operating system needs to be able to control, all right, these different processes and when they're actually going to be executed. All right, this is done through the use of what are known as process descriptor blocks. Essentially, these process descriptor blocks give the operating system kernel an idea of what that particular process is all about. So first and foremost, it knows the process ID, whether or not it is in the ready state, in the block state, all right, where it is within the program counter, all right, its current context, essentially what are the current values of the CPU registers for it to continue in the next time slice. All right, its priority, for example, for more scheduling information, as well as additional information about memory, all right, currently allocated to this particular process, how much time has been used by the CPU for this particular process, and also what devices are actually linked to this particular process at any given point in time. Maybe it is trying to open a particular file, maybe it is trying to send a particular file, maybe it has a particular I/O device, like a game controller, for example, linked with that particular device. These are all the different pieces of information that are stored within a process descriptor block. Okay. Now, one of the very important things that one needs to do whenever you are handling processing is scheduling. Essentially, the idea is to keep the computer multitasking and multiprocessing and make sure that real-time processes actually are run in a fashion that makes that would execute in the correct amount of time. All right. Essentially, what we're doing with scheduling is we are dictating, all right, which processes are going to be run, when, and where, and for how long, essentially. And there are a number of different routines, all right, that the operating system can perform in order to carry out these scheduling tasks. And these are actually handled by what are known as schedulers. There are different kinds of schedulers, all right. But in essence, these schedulers' job is in order to make sure that the CPU utilization is as busy as possible, that you have as many processes completed as possible, that you are being able to turn around, all right, the number of processes in as short amount of time as possible, that each process doesn't end up waiting invariably, that it responds as quickly as possible to these processes, as well as being fair to each and every process without actually starving it out for CPU attention, essentially. All right. This is even more important, especially when it comes to real-time environments. All right. So in real-time environments, all right, the scheduler must ensure that these processes are actually done by certain deadlines. Okay. Now, as I said, there are different types of schedulers. There's the long-term scheduler, all right? The long-term scheduler is essentially the scheduler that is going to admit new processes into the queue for it to become executed. Essentially, this scheduler dictates which processes are going to be run in which order on the CPU. If you have multiple cores to the CPU, it will also determine which CPU is actually going to be working on which process at any given point in time. All right. However, since this is a long-term scheduler, and this is essentially when you're actually going to admit the new processes into the CPU for the very first time, it doesn't necessarily need to be invoked as frequently. It usually is not the fastest scheduler that you have, because essentially new processes are only going to come up once every so often, so it doesn't necessarily need to be that fast. All right. On the other hand, the short-term scheduler is a scheduler that needs to execute very, very, very quickly. Essentially, the short-term scheduler is the scheduler that is actually going to indicate which processes are actually going to be given a time slice in order to be able to execute in order to be able to execute the process itself. Essentially, the short-term scheduler is called much more frequently than the long-term scheduler, and as we're going to be seeing, the mid-term scheduler, and therefore it needs to be the fastest of the lot. Now, these types of schedulers, these short-term schedulers, can again fall into two categories. You have what is known as a preemptive scheduler and a non-preemptive scheduler. We're going to be seeing what that means in a moment. Okay. You have the midterm schedulers. The midterm schedulers are schedulers that essentially involve maintaining main memory with regards to secondary memory and vice versa, especially when it comes to swapping in and swapping out pages. Essentially, whenever that page fault comes across, it is its job to take into account which pages needs to be swapped out from main memory and which pages from secondary memory needs to be swapped back into main memory. So essentially, the middle term scheduler is what is actually keeping track of your virtual memory space. All right. And finally, you have your I/O scheduler. Your I/O scheduler is essentially the scheduler that is going to be associated with with I/O operations, and usually when we talk about I/O operations, in this case, we're usually talking about disk scheduling. All right, essentially, we're talking about when an I/O device is going to request attention from the CPU and vice versa. All right. So essentially, the whole point behind the I/O scheduler is to make sure that the I/O device doesn't waste time. All right, when it's actually reading data. In the case of a hard disk, when it's seeking data, it prioritizes which I/O requests go first. It also make sure that the disks are given enough bandwidth in order to run a process more effectively, and it tries to guarantee that each device is actually serviced by some form of deadline system. All right. So when we're scheduling these processes, all right, we create a number of queues, all right, in order to help the management of these different processes at any given point in time. You have the job queue, which is attached to the long-term scheduler, all right? Essentially, it is all of the new processes that are going to be added to the system. You have the ready queue, which is a queue of all of the processes that are waiting in main memory to be given a time slice so that they can actually start executing. You have your IO queue, all right, which is basically a list of processes that are waiting for a particular IO device to become available. And you have your intermediate queue, which is basically a list of processes that have been swapped in and swapped out of disk, okay, so within virtual memory. All of these queues do not necessarily follow a first in, first out basis. So they can also be what is known as a priority queue. All right. So it's not like a normal queue. All right. Sometimes priority actually takes precedence in this case. All right. So essentially, when a new process comes in, it goes into the ready queue. All right. When a process is going to be executed, it is dispatched to the CPU. All right. If it is finished executing, it will exit. All right, and therefore terminate. If the time slot given to that CPU to that process is over, then essentially it will go back into the ready queue. If, for instance, that process is waiting for a particular event, it would go into an event queue. All right. If it's waiting for an IO event, it will go into an IO queue. If it is being swapped in or swapped out, then it might go even into an intermediate queue. All right. Now, I talked about the idea between preemptive and non-preemptive. All right. So the short-term scheduler, as I mentioned, can actually have what is known as a non-preemptive multitasking approach. Essentially, what this means is that the program or the process itself is going to determine, all right, when it's going to relinquish the CPU or the system resources to yet another process. So essentially, this kind of scheduler would require that the processes themselves not hog, all right, the CPU resources, and at some point in time cooperate with other processes and say, all right, I'm going to relinquish the CPU resources to another process so that it can continue executing. All right. Essentially, it is the process that is actually going to determine when it is actually going to interrupt itself from executing. So essentially, that's why it's known as cooperative or voluntary. Okay. Preemptive scheduling, on the other hand, is when we actually dictate to the process how much time it's actually going to be given in order to execute a particular process. One of the most efficient ways that this is done is by giving time slices, all right, or time quantums, if you will, to each and every process. All right. Once that time is up, you move on to the next process. All right. Essentially, in order to make sure that every process gets its fair share, all right, you would give an amount of time slices to these processes in order to be able to execute as rapidly as possible. All right. Now, the short-term scheduler might also have what are known as scheduling policies in order to make sure that CPUs will execute as many processes as quickly as possible. Now, there are schedulers which are non-preemptive, all right, and have other schedulers which are preemptive. The non-preemptive include the first in, first out, the shortest time remaining, and the fixed priority scheduling, whereas the preemptive approach can be the round robin approach. Let's see what each and every one of these means. So the first in, first out, or first served scheduling approach essentially means that any process that comes in is going to be executed to its entirety, all right, until it moves on to the next process. All right, that is essentially the idea behind it. Obviously, this means that the process can be a long one, and therefore it can hog the CPU for quite a substantial amount of time, which means that the turnaround time is actually going to be quite slow. All right, and therefore it could be the case that you could have certain processes that become starved, all right, of CPU time, for the simple reason that a particular process can be stuck in an infinite loop, which means that other processes that came after that will never actually be able to see the CPU the CPU time slot, essentially. The shortest job first scheduling process, basically what it does is it receives processes, all right, and it executes the process with the smallest amount of time remaining first, all right. If it is working on a process currently and another process with a shorter duration comes in first, it will take precedence and it will execute first. Essentially, the idea is that it takes advantage of these short processes as they are handled very quickly, meaning that it's going to get rid of a lot of smaller processes very, very, very quickly. However, it also means that longer processes might take some time in order for them to actually get executed, because a number of different smaller processes might always cut it up, and therefore they might be starved because they are not actually giving any CPU time whatsoever. Another approach is to have sort of like a fixed priority preemptive scheduling, essentially whereby you would give each process a priority number, and you would literally execute those processes which have a higher priority number over the others, all right, because they are more important, all right. The problem is that if the priority is fixed and it doesn't actually update itself, all right, as in it becomes more and more severe as time goes by, then it means that you can have processes with very low priorities which will also starve because they won't actually be given any time in order to be able to execute either. All right. So what you could do is you could also have a varied priority scheduling process where essentially each process will actually increment in their would increment their priority the longer they stay within the queue, essentially. Kind of like what happens at hospital, if you think about it. Okay. And finally, we can also talk about the round robin approach. The round robin approach, on the other hand, is a preemptive policy. Essentially, it requires that each process uses a certain amount of time. All right. Once that amount of time is up, you would move on to the next process and the next process and the next process. If you haven't finished executing, you will go back to the queue and you will wait, all right, for the next time slot that it becomes available. The good thing about the round robin approach is that it is very simple in order to implement, all right, and it's also starvation free. Why? Because at any given point in time, a process is actually going to be given a time slot and it's eventually going to execute. All right, that's the whole point behind the round robin approach. All right. In fact, it is one of the better approaches because it sort of like combines the best of both worlds with regards to the first come, first serve and the shortest job first. In fact, it is faster than the first come first served scheduler strategy when it comes to longer processes, but it is faster than the shortest job first when it comes to longer processes. So it depends on which point of view you're looking at it from. So for shorter jobs, it is faster than the first come first served. For longer jobs, it is faster than the shortest job first. All right. The only main problem with this system is that deadlines aren't really met with the round robin approach. All right. But the good thing is that starvation can never occur. All right. The important thing behind the round robin approach is the idea of the time slice. So essentially, you're given each process an amount of time, all right? So 10 milliseconds, 100 milliseconds, in which case that process is actually going to be making use of the of the computer's resources, all right? Three things can happen when you're running a process. The process can terminate before that time slice is up, in which case you would discard the remaining time and you would move on to the next process. It could also be the case where the process, all right, during its time slot would require some IO access or some file access or whatever, in which case it would become blocked. In which once it becomes blocked, it stops there, moves it into the blocked queue, and it would move on to the next process, or it finishes the entire process, all right, or the entire time slot, sorry, in which case it will be preempted, all right, so that it would actually give time to the next process, essentially. Okay, and this is a basic overview of these different scheduling policies and how they actually work in relation to CPU utilization, throughput, turnaround time, response time, deadline handling, and starvation, whether or not they are starvation free. Okay, that is basically all that I have for you for this year. Thank you very much for being so patient with me, all right, and staying with me till the end, all right. I know that it's a late night as well. I wish you a very, very, very I wish you the best of luck within your examinations, all right, and in our next term we will be able to look to revising all of the different topics that we've actually covered throughout our first and second terms, all right, to help prepare you better for your final examinations. All right. Thank you very much. Good night.
Thank you, sir.
Bon
Thank you,
appetit.
sir. Good night.
Thank you, sir. Good night.
Good night. Don't forget to punch out.
Yes.
Okay,
Thank
thanks
you.
a lot.
Thank you.
Thank you.